welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 733, flood fill. This is a popular problem that tests your understanding of depth-first search, DFS, or breadth-first search, BFS, algorithms, and how to apply them in grid-based scenarios. Let's dive in. Flood fill is a classic algorithmic problem where we start with an image represented as a 2D grid of integers. Each entry in this grid corresponds to a pixel in the image, and the value of the entry represents the pixel's color. Along with the image, we are given three additional inputs: SR, the row index of the starting pixel, SC, the column index of the starting pixel, and color, the new color we want to apply. The goal is to modify the image by replacing all pixels that are connected to the starting pixel and share the same initial color as the starting pixel. These connected pixels must be connected in one of the four cardinal directions: up, down, left, or right. After performing this replacement, we return the updated 2D grid as the result. To better understand the problem, let's look at an example. Suppose the input image is a 3x3 grid where most of the pixels have a value of 1, except for a few that are 0. The starting position is 1, 1, and the new color is 2. Starting from the pixel at 1, 1, which has a value of 1, we look at all four directionally connected pixels that also have the same value of 1. These pixels are updated to the new color 2. The output is a modified grid where the connected region of 1s has been replaced with 2s, while the unconnected 0s remain unchanged. To explain this example further, at position 1, 1, the pixel value is 1, which matches the criteria for replacement. From there, we move in all four directions to find other connected pixels with the same value of 1. These include positions like 0, 1, 2, 1, and so on. Each of these is updated to 2. The result is an image where the connected region has been entirely replaced. Now consider another example, where the image is a 2x3 grid of 0s, and the starting position is 0, 0. Here, the starting pixel already has the same value as the new color, which is also 0. Since there's no need for any changes, the output remains the same as the input. In the next example, the input image is a 3x3 grid, and the starting position is 1, 1, with a new color of 3. The pixel at 1, 1 has a value of 0, and no other four directionally connected pixels share this value. Therefore, only the starting pixel is updated to 3, and the rest of the image remains unchanged. This demonstrates that the flood fill operation only propagates through pixels that are directly connected and share the same original value as the starting pixel. The problem also specifies several constraints to ensure the solution handles all edge cases. The dimensions of the image, m and n, are between 1 and 50, meaning the grid can be as small as a single pixel or as large as 50 by 50. Each pixel value, as well as the new color, can range from 0 to 10^4, so the solution must handle large integer values efficiently. Additionally, the starting indices SR and SC are guaranteed to be valid positions within the grid. These constraints ensure the problem is well defined and that the solution must handle both small and large cases robustly. Finally, there are several edge cases to consider. For example, no change occurs if the starting pixel's value is already equal to the new color. The algorithm must also handle minimal image sizes, such as a 1x1 grid, and ensure there's no integer overflow with large color values. In cases where the entire image is fully connected with the same value, a flood fill will update all pixels. Conversely, in images with disconnected regions, the flood fill must only affect the region connected to the starting pixel, without spilling over into other areas. These details are critical for implementing a correct and efficient solution. To solve the flood fill problem, let's first consider a brute force method. The intuition behind this approach is to iterate through the entire 2D grid and change every cell that matches the target color, which is the color of the starting cell at position, SR, SC, to the new color. While this might seem reasonable initially, it quickly becomes inefficient. The brute force method doesn't take advantage of the fact that the flood fill operation only spreads to connected cells. As a result, we end up processing many cells unnecessarily, even those that have no relevance to the starting point. This inefficiency and lack of connectivity awareness make the brute force method impractical for larger grids. Now, let's look at a more structured approach using depth-first search, or DFS. The intuition here is to leverage the natural connectivity of the grid. DFS starts at the given cell, SR, SC, and recursively explores all its neighbors up, down, left, and right, updating their color if they match the original color. This process ensures that only relevant connected cells are updated. The key insight here is to treat the grid as a graph, where each cell is a node connected to its neighbors. DFS, being a graph traversal algorithm, is a perfect fit for solving this problem. To implement this, we follow a few key steps. First, record the original color of the starting cell. Next, check if the current cell's color is already the target color, in which case we can immediately return. If not, we use recursion to update all connected cells while ensuring we remain within grid boundaries. This structured approach respects both the connectivity constraints and the problem's requirements, making it much more efficient than brute force. Analyzing the complexity of these approaches, DFS has a time complexity of n*m, where n and m are the grid dimensions. This is because, in the worst case, we might visit each cell exactly once. For space complexity, it can also reach n*m, due to the recursion stack, especially in scenarios where all cells in the grid are connected. Another approach worth considering is breadth-first search, or BFS. Instead of recursion, BFS uses a queue to iteratively process cells. Starting from the cell, SR, SC, the algorithm enqueues the starting cell, updates its color, and then processes its neighbors iteratively until the queue is empty. This method is also efficient, with the same time complexity of n*m. However, BFS requires additional memory for the queue, which can be a drawback compared to DFS. When comparing the two, the choice often comes down to practical considerations. DFS aligns naturally with the recursive structure of the problem, making it simpler to implement and understand. On the other hand, BFS avoids potential stack overflow issues by eliminating recursion and using an iterative approach. Ultimately, we chose DFS as the primary strategy for this problem. It is conceptually straightforward, directly matches the recursive nature of flood fill, and avoids the additional memory overhead associated with maintaining a queue in BFS. While DFS does have the potential risk of stack overflow for extremely large grids, this is generally not a concern in most practical scenarios. BFS is still a valid alternative for edge cases where recursion depth might be an issue. Given these considerations, our final strategy is to implement DFS as the default solution for the flood fill problem due to its simplicity and efficiency. However, in edge cases where stack overflow might occur, BFS can serve as a backup option. To bring this approach to life, we can use the following pseudocode. The function floodFill begins by recording the original color of the starting cell. If this color is already equal to the new color, we simply return the image as is. Otherwise, we define a helper function DFS, which performs the recursive traversal. This helper function ensures that we only process cells within bounds that match the original color. At each step, the cell's color is updated, and its neighbors up, down, left, and right are recursively processed. The traversal continues until all connected cells have been updated. This implementation ensures that the flood fill operation is performed efficiently and correctly, meeting all the constraints of the problem. By incorporating boundary checks and focusing only on connected cells, we achieve a solution that is both robust and elegant for this graph traversal challenge. Flood fill is a classic algorithm often used in graphics applications to modify a specific region of an image. The goal is to start at a given cell, SR, SC, and recolor the entire connected region of cells that share the same color as the starting cell. To do this, we replace their color with a new specified color. To begin, we validate the input. If the image grid is empty, we terminate immediately since there's nothing to process. Similarly, if the starting cell already has the new color, there's no need to make any changes, so we simply return the grid as it is. Next, we define some key variables. First, we determine the target color, which is the original color of the starting cell. This is the color we'll be replacing in the connected region. We also store the new color, which is the replacement color, and calculate the dimensions of the grid, rows, and calls. Now, to initiate the algorithm, we use a breadth-first search approach. A queue is initialized to keep track of cells to process, starting with the initial cell, SR, SC. We immediately mark this cell as visited by changing its color to the new color, which ensures that we avoid processing it again later. To explore the grid systematically, we define the possible movement directions, which include moving up, down, left, and right. These directions can be represented as coordinate changes: 0, 1 for moving right, 1, 0 for moving down, 0, -1 for moving left, and -1, 0 for moving up. Once the directions are defined, we process the queue. While the queue is not empty, we dequeue a cell, X, Y, and examine its neighbors by applying each of the movement directions. For each potential neighbor, NX, New York, we check if it is within the grid bounds and if its current color matches the target color. If both conditions are satisfied, we recolor the neighbor cell with the new color and add it to the queue for further processing. This systematic approach ensures that all connected cells are processed. The algorithm concludes when the queue is empty, meaning that all reachable cells with the target color have been recolored. At this point, we return the updated grid as the final result. This approach ensures efficient processing while maintaining correctness. One key insight here is how connectivity is handled. Only cells directly connected to the starting cell and having the same target color are considered. This prevents unnecessary recoloring of unrelated regions. Another important aspect of this algorithm is the way it avoids cycles. By marking cells as visited as soon as their color is changed, we prevent the same cell from being added to the queue multiple times, which ensures that the algorithm terminates correctly. Additionally, the algorithm is robust enough to handle edge cases, such as when the starting cell already matches the new color, when the grid contains only one cell, or when there are disconnected regions of the same color. In terms of data structures, the queue plays a central role by enabling the breadth-first search. This structure ensures that cells are processed level by level, which is systematic and avoids the potential pitfalls of recursion, such as stack overflow. The grid itself is directly modified during the algorithm to mark cells as visited, which reduces space complexity since no additional structure is needed for tracking visited cells. When analyzing the complexity, the time complexity is O, n asterisk m, where n and m represent the number of rows and columns in the grid, respectively. This is because every cell is processed at most once. The space complexity is also O, n asterisk m in the worst case, which occurs when all cells in the grid are part of the connected region and need to be stored in the queue at some point. To better understand the algorithm, let's walk through an example. Suppose the input grid is 1, 1, 0, 1, 0, 0, 0, 0, 1, with the starting cell 0, 0, and a new color of 2. The target color in this case is 1, which is the color at 0, 0. We begin by changing 0, 0 to 2 and enqueuing its valid neighbors. The next cells to process are 0, 1, and 1, 0, which are directly connected to the starting cell and share the same target color. These cells are also recolored to 2, and their neighbors are enqueued if they meet the criteria. This process continues until all connected cells with the target color have been recolored. At the end of the algorithm, the updated grid becomes 2, 2, 0, 2, 0, 0, 0, 0, 1. This output shows that only the region connected to the starting cell has been modified, while the rest of the grid remains unchanged. This example highlights the efficiency of the BFS approach, as it systematically processes every connected cell without revisiting or modifying unrelated parts of the grid. Here, we begin by defining a function called floodfill inside the solution class. This function takes 4 parameters: the image represented as a 2D list, the starting row and column coordinates SR and SC, and the new color that we want to apply. The first step is to extract the current color of the starting pixel using image, SR, SC. This will help us determine which pixels we need to change. Next, we check if the starting pixel's color is already the same as the new color. If it is, there's no need to proceed further, so we simply return the image as is. We then calculate the dimensions of the image by determining the number of rows and columns. These will help us ensure that we stay within the bounds of the image during our traversal. To perform the flood fill, we define a helper function named DFS, which stands for depth first search. This function will recursively explore the image. Inside the DFS, we first handle the base case. If the current cell is out of bounds or does not match the starting color, we simply return, as there's nothing to process for that cell. If the current cell is valid, we update its color to the new color. Afterward, we recursively call DFS on all four neighboring cells, down, up, right, and left. This allows us to explore and change all connected pixels with the starting color. Now that the DFS function is defined, we initiate the flood fill process by calling DFS with the starting coordinates SR and SC. This triggers the recursive traversal, and every connected pixel matching the starting color will be updated to the new color. Once the recursion completes, all relevant pixels in the image will have been processed. Finally, we return the modified image as the result. This approach ensures that the flood fill is performed efficiently, covering all connected areas while avoiding unnecessary computations. The recursive nature of the solution makes it clean and easy to understand, as it systematically explores all valid paths in the image. By the end, the image will reflect the desired changes, with all connected regions updated as specified. Here, we start with the Java implementation of the flood fill algorithm. The method flood fill takes three inputs: the image represented as a 2D array, the starting row and column indices, and the new color we want to apply. First, we retrieve the current color of the starting pixel using image SR, SC. Then, we check if the starting pixel already has the new color. If it does, there's no need to proceed further, so we simply return the image as it is. Next, we determine the dimensions of the image by storing the number of rows and columns. To handle the actual flood fill logic, we define a helper method called DFS that will perform a depth-first search. This recursive method will explore and update the image. Finally, we call this DFS method with all the necessary parameters, and once it's done, we return the updated image. The DFS helper method begins by checking the base case. If the current cell is out of bounds or if the color of the cell does not match the starting color, we simply return and stop processing that cell. Otherwise, we proceed by updating the color of the current cell to the new color. After this, we recursively explore the four possible directions: down, up, right, and left. For each direction, we call the DFS method with the updated row or column indices while passing along the image dimensions, starting color, and new color. This ensures that the algorithm continues to propagate the new color to all connected pixels that originally shared the starting color, effectively performing the flood fill operation. To begin solving the flood fill problem, we focus on this basic case. The input image is a 3x3 grid, and the starting pixel is located at position 1, 1, with a value of 1. This value is stored as the starting underscore color. Since the starting underscore color is not equal to the new color, which is 2, we proceed with the algorithm. A helper function, DFS, is defined to perform depth-first search, and we note that the image dimensions are 3 rows by 3 columns. Starting from 1, 1, we change its color to 2, and then explore its neighbors, 2, 1, 0, 1, 1, 2, and 1, 0. Moving to the neighbor, 2, 1, we observe that its color is 0, which does not match the starting underscore color of 1, so no further action is taken for this neighbor. Now, we move to the next neighbor, 0, 1. At this position, the color is changed to 2, and we explore its neighbors, 1, 1, minus 1, 1, 0, 2, and 0, 0. The pixel at 1, 1 has already been visited, and minus 1, 1 is out of bounds, so we skip them. Moving to 0, 2, we change its color to 2, and since all its neighbors lead to termination, we backtrack. Next, we visit 0, 0, change its color to 2, and again, all its neighbors lead to termination. Finally, we backtrack to the neighbor 1, 0. Here, we change the color to 2 and explore its neighbors, but no further changes are needed as they all lead to termination. The updated image after completing this process looks like this: 2, 2, 2, 2, 2, 0, 1, 0, 1. In this example, we consider a case where no changes are needed. The input image is a 3x3 grid where every pixel has a value of 0. The starting pixel is at position 1, 1, with a value of 0, which is stored as the starting underscore color. Since the starting underscore color is equal to the new color, which is also 0, there is no need to modify the image. The algorithm terminates immediately, and the original image is returned as the result. The final image remains unchanged, 0, 0, 0, 0, 0, 0, 0, 0, 0. This example demonstrates how the algorithm handles an isolated region. The input image is a 3x3 grid where the central pixel at 1, 1 has a value of 1, while all other pixels are 0. The starting pixel is 1, 1, and its value is stored as the starting underscore color. Since the starting underscore color is not equal to the new color, which is 2, we proceed with the flood fill. Beginning the depth first search from 1, 1, we change its color to 2 and explore its neighbors, 2, 1, 0, 1, 1, 2, and 1, 0. Moving to 2, 1, the color is 0, which does not match the starting underscore color, so no further action is taken for this neighbor. Similarly, all other neighbors, 0, 1, 1, 2, and 1, 0, also have a color of 0, which does not match the starting underscore color. As a result, no further actions are taken, and the algorithm terminates after processing the central pixel. The final image reflects the isolated region being filled 0, 0, 0, 0, 2, 0, 0, 0, 0. The time complexity of the flood fill algorithm is O(m*n), where m represents the number of rows in the image, and n is the number of columns. This is because, in the worst-case scenario, the algorithm may need to visit each pixel in the image exactly once. This happens when all pixels are the same as the starting color, requiring every one of them to be processed and changed to the new color. For each pixel, the algorithm performs a constant amount of work. It changes the pixel's color and recursively calls the DFS function on its neighbors. These operations collectively result in a time complexity proportional to the total number of pixels in the image, which is m multiplied by n. Additionally, the boundary checks and color matching comparisons are constant time operations, O(1), performed during each DFS call. However, since these checks are repeated for each pixel, their contribution is ultimately dominated by the same O(m*n) complexity. Now, let's consider the different cases for time complexity. In the best-case scenario, if the starting pixel's color is already equal to the new color, no changes are needed, and the algorithm terminates immediately. This results in a time complexity of O(1), as no recursion occurs. In the average case, the algorithm typically processes a subset of pixels that are connected and share the starting color. If we denote the size of this connected region as k, the complexity in this case becomes O(k). Finally, the worst-case scenario occurs when all pixels in the image are connected and require processing. Here, the algorithm visits every pixel, leading to the maximum time complexity of O(m*n). Moving on to space complexity, the algorithm's space usage is determined by the recursive call stack. Since it uses DFS, each recursive call adds a frame to the stack. In the worst case, where all pixels are connected, the recursion depth can grow to the size of the entire image, resulting in O(m*n) space usage. In addition to the call stack, it's important to note that the flood fill algorithm modifies the input image directly. This means no additional memory is allocated for storing the image or the result, which contributes only O(1) extra space. Considering the best-case scenario for space complexity, if no recursion occurs, such as when the starting pixel's color already matches the new color, the algorithm uses only O(1) space. For the average case, the recursion depth corresponds to the size of the connected region, denoted as k. Thus, the space complexity in this case is proportional to O(k). In the worst case, where the entire image is a single connected component, the recursion depth grows to match the total number of pixels, leading to a space complexity of O(m*n). This balance between in-place modifications and recursive stack usage ensures the algorithm remains efficient in both time and space. Comparing the flood fill algorithm with a naive approach highlights its efficiency. A naive approach might involve iterating over the entire image and checking every pixel against the starting color. This would result in a time complexity of O(m*n), regardless of the connectivity of the region. Additionally, if a separate array is used to store the output, the space complexity would also be O(m*n). In contrast, the flood fill algorithm, using DFS, limits its processing to only the connected region that matches the starting color. This avoids unnecessary work on unrelated pixels and ensures that the operation is focused and efficient. Furthermore, it modifies the image in place, eliminating the need for additional storage. In summary, while both approaches have a worst-case time complexity of O(m*n), the DFS approach is more efficient for smaller connected regions. Similarly, the space complexity for DFS is O(m*n) in the worst case, but it offers reduced space usage for smaller regions by leveraging in-place modifications. When working on flood fill or similar algorithms, there are several common mistakes to watch out for. First, always check your base cases. For example, if the new color is the same as the original color, there's no need to proceed with recursion. Forgetting this can lead to infinite recursion or unnecessary computations, wasting both time and resources. Another mistake involves directly modifying the grid while iterating, especially during recursive calls. Without proper boundary checks, this can overwrite data you still need or cause you to skip over certain cells. Speaking of recursion, if you don't mark visited cells correctly in a depth-first search, it's easy to revisit the same cells endlessly, which can result in Stack Overflow errors or excessive runtime. Additionally, boundary validation is critical. If you fail to ensure the indices are within the grid's bounds, you may encounter index out-of-bounds errors that crash the program. Lastly, always consider performance. A brute force solution might work on small grids, but for something like a 10,000 x 10,000 grid, it could become impractically slow. Optimizing your approach for scalability is key, especially during an interview scenario. Now, when preparing for interviews, there are a few important insights to keep in mind. Recognizing patterns is crucial. Many grid-based problems, including flood fill, can be solved using techniques like depth-first search, breadth-first search, or even union find. Quickly identifying which strategy to use can save valuable time. Interviewers often focus on how you optimize your solution after presenting a brute force approach, so be ready to discuss trade-offs and improvements. Handling edge cases is another common area of evaluation. Be prepared to address scenarios like empty grids, single-cell grids, or cases where no changes are needed. It's also worth discussing space versus time trade-offs. For example, using recursion leverages the call stack but increases space complexity, while an iterative approach with an explicit stack might reduce that overhead. Finally, familiarity with related problems is helpful. For instance, problems like max area of island, number of islands, and O1 matrix share similar traversal patterns, and understanding these can strengthen your problem-solving skills. To solve flood fill problems, there are several alternative approaches you can consider, each with its own trade-offs. Depth-first search, or DFS, is a straightforward method that's simple to implement. However, it relies on the call stack, which can lead to stack overflow for very large grids. Its time complexity is O(n*)m, where n and m represent the grid dimensions. Breadth-first search, or BFS, avoids this issue by using an explicit queue, making it a safer option for larger grids. While slightly more complex to implement than DFS, it shares the same O(n*)m time complexity. Another option is union find, which is particularly useful for handling problems with multiple queries. Although it's more complex to implement, it offers a time complexity of O(n*)m plus q*log*(n*), where q represents the number of queries. Lastly, there's the brute force approach. While it's the simplest to understand and implement, it's also the least efficient. For large grids, its O(n*)m*, k complexity, where k is the number of connected components, makes it impractical. Understanding these methods and their trade-offs allows you to choose the most suitable approach for the problem at hand. Great job working through this problem. In summary, flood fill is a classic example of grid traversal using DFS or BFS. We discussed its time and space complexities, as well as some practical takeaways. Don't forget to practice similar problems to reinforce your understanding. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!